Hello everyone. Our topic is B tree and KD tree. So this is the roadmap and we have split the roles amongst ourselves like shown in the slide. I am Pranave, software developer of B tree. So what is B tree exactly? B tree, also called as balanced tree data structure, renowned for efficiently storing and managing sorted data. You can look at the slide to know how a B tree will look like. This arrangement enables sufficient and efficient traversal and search operations, as keys can be quickly located within each node. One important property of B-tree is that all leaf nodes are at same level. The advantages of B-tree include balanced structure, efficient operation, and the main disadvantage is it having a complex algorithm for insertion and deletion, so comparatively slow to other data structures. Applications of B-tree include database system, file system, and B-trees are also utilized in web browsers to store and manage bookmarks, history, and cache data. So let me uh, give you the coding part of B-tree. So first, the class definition. So in class definition, maximum keys refers to the maximum keys a node can hold. Each key corresponds to a value, and max children refers to maximum children a non-leaf node can hold. So the general equation is max children equal to max keys plus 1. For the struct node part, n represent current number of keys, and there is an array of keys, an array of pointers pointing to a child node, and it also represents whether the node is a leaf node or not. So first let me explain how a value gets inserted in the B tree. At first the B tree is empty. So first value becomes the root using a create node function which creates the node according to the struct part and also mentions if it is a leaf node or not. And now when we try inserting another value, it first checks if root node is full. If not, insert non-full function is called and it inserts the value in B tree in a sorted way. During the insertion process, if a node becomes full, split function is called. To split the full node, a new node is created to accommodate the overflow of keys. The new node will eventually become a sibling of the original node. The median key of the full node is selected. This is the middle key when the keys are sorted. The median key is moved up to the parent node, and this is done to maintain the ordering of keys in the parent node. The keys in the full node, excluding the median key, are distributed evenly between the original node and new node. If the original node has an odd number of keys, one of the nodes might have one more key than the other. The new node is connected to the parent node in the appropriate position based on the median key that was moved up. The split child operation ensures that B tree remains balanced and maintain its property, such as maximum number of keys per node and minimum degree of the tree. Now that we have completed insertion, let's have a look at the search function and display function. First, the display function. This function displays the keys stored in B-tree node and its children. It traverses through the node's keys and recursively displays its children if it is not a leaf node. The keys are printed in ascending order and child nodes are explored recursively for each key. Next, the search function. It traverses through the keys of a node to find the appropriate child node. If the number is found in the current node, it returns the node. Else, if the number is not found at the node, which is a leaf node, it returns null. Otherwise, it continues searching recursively in the appropriate child node. Now let's see how deletion works in B-tree. The function deletion removes a specified value from a B-tree. It searches for the value recursively and handles deletion based on whether the node is a leaf or not. If the value is found, it deletes it from the leaf node directly. Otherwise, it traverses through the appropriate child node. After deletion, it ensures that the B tree properties are maintained and handles cases where the nodes become underfilled or the value is not found in the tree. So the functions such as get predecessor and get successor locates the largest key that is less than the given key and locates the smallest key that is greater than the given key respectively by traversing to the rightmost leaf node of the left subtree of the node containing the specified key or the right subtree. Remove from non-leaf function is used when we first check if the left child has enough keys? If yes, we replace the target key with its predecessor and delete it. If not, we check the right child for enough keys. If found, we swap the target key with its successor and delete it. If neither child has enough keys, we merge the current node with its adjacent child and recursively remove the target key from the merged child node. The functions such as borrow from previous and borrow from next specify how to shift a key from the left or right sibling respectively to the current node at a specified index to address a key shortage during deletion. The merge function, it moves a key from the parent node into one of the child node to ensure each node has enough keys. Then it combines the keys and child pointers from the two child node into one, updating the parent node accordingly. The last function is the fill function in the B tree, which plays a crucial role in maintaining balance and structure. When a deletion operation is called, it leaves a node with fewer keys than required. So fill is used. It first checks the neighboring nodes to see if they have surplus keys that can be borrowed. If the left child node has enough keys, it borrows one from there. If not, it checks the right child node. If borrowing from neighbors isn't an option, fill merges the current node with one of its adjacent child node. After borrowing or merging, the function recursively handles any necessary deletions in the affected child node to uphold the balance throughout the tree. So all these functions help maintaining the structure of B as well as deleting the key.
Hello guys, I'm Pranav B and I'm going to talk about KD trees. Imagine you have a collection of points in a multi-dimensional space, each defined by its coordinates. The KD tree is a hierarchical data structure designed to organize these points efficiently, particularly in higher dimensional spaces. At its core, a KD tree is a binary tree where each node represents a point in the space. The key idea behind the KD tree is to partition the space along alternating axes, creating a binary partitioning in each dimension. This alternating partitioning enables fast search operations by efficiently narrowing down the search space. Now I'm going to talk about advantages and disadvantages of KD tree. The advantages of KD tree is that it allows for efficient k-nearest neighbor queries, which are useful in image recognition and recommendation systems. They can also be used for range queries, which allows for fast searches of points within a given radius. However, there are also several disadvantages to using KD trees. Whenever, the, Whenever there are higher dimensions, it becomes inefficient due to a phenomenon called curse of dimensionality. This occurs because as the number of dimensions increases, the volume of the space between points increases exponentially, making it difficult to capture the geometric relationship between points accurately, thereby increasing the difficulty for insertion and searching for a node. Additionally, the performance of a KD tree can be highly sensitive to the choice of splitting axis and point selection strategy. KD trees may not perform well when the data is highly skewed or has a complex distribution, in which case some other data types are much faster. For example, cover trees and ball trees. Now I'm going to speak about the algorithms of the code. Let's start with insertion. The insertion process in the KD tree class involves creating a new node to represent the point being inserted. The new node function initializes a new node with the provided coordinates and assigns it as the root if the tree is empty. In the insert function, the insert recursive helper function is called to traverse the tree and find the appropriate position for insertion based on the current node's coordinates. The tree is traversed depth by depth, alternating between dimensions until a suitable leaf node is found. The new node is then attached as either the left or right child of the leaf node based on a comparison with the current node's coordinates value along the relevant dimension. After insertion, I am going to talk about the search algorithm. In the search operation of the KD tree structure, we traverse the tree recursively from the root node, comparing the search point with the current node's point along the relevant dimension determined by the current depth modulo the number of dimensions. So which is the formula? If a match is found indicating that the point exists in the tree, we return true. Otherwise, we continue the search recursively in either the left or right subtree based on the comparison result until reaching a leaf node or encountering a null node, signifying that the search point is absent. During this process, the findMinRec function plays a crucial role in finding the minimum node along the specified dimension, recursively searching for the minimum node by comparing nodes along the given dimension and selecting the minimum among the current node, the minimum node in the left subtree and the minimum node in the right subtree. This ensures efficient search and retrieval of the nodes within the KD tree data structure. Additionally, the min_node function aids in comparing nodes to determine the minimum among them. Now I'm going to talk about the deletion algorithm. The deletion operation in the KD tree class involves finding and removing a specified point from the tree. The delete node function checks if the point to be deleted exists in the tree using the search function. If the point is found, the delete node recursive helper function is called to traverse the tree and locate the node corresponding to the point. Once the node is found, different scenarios are handled based on the node's children. If the node has 2 children, the minimum node from the right subtree is selected to replace it, ensuring the tree remains balanced. If the node has only 1 child, that child is promoted to take the node's place. If the node is a leaf node, then it is simply removed from the tree. Now let's look at the time complexities between these different data structures and compare those. Performance trade-offs, B tree and KD tree. So when we look at the diagram, we clearly understand the time complexities of different data structure. In B tree, the insertion is constant O of log, big O of log n. But in KD tree, the average case is big O of log n. But when the dimension increases exponentially, if we have higher dimensions, then the worst case can become big O of n. Similarly, in B tree, search operation is also big O of log n. And in KD tree, on average, it is big O of log n. But if the dimension increases or the input by the user increases, then worst case happens, the time complexity becomes big O of n. Similarly, it can be said for deletion and space complexity. Now let's come to the balancing part. B tree requires frequent rebalancing operations. So it may take much time, but KD trees don't require such rebalancing operations, but it may become unbalanced depending on the input data. So these are all the difference between B tree and KD tree, and they both have different functionalities. I would like to conclude by saying that we have defined B tree and KD tree, and these are its time complexities. Thank you.
So make sure to like, share, and subscribe, guys.